Hi, I'm Aurora Wild. Welcome back to my astrophysics lesson series. On this channel so far, we've covered Newtonian gravity, general relativity, black holes, dark matter, and dark energy. Today, we're covering general relativity's sister theory, special relativity.
Einstein was really young when he started thinking about questions of special relativity. He famously did a thought experiment when he was about 16, where he imagined he was riding on a light beam going the speed of light. If there was an identical light beam next to him, he wondered if it would appear to move at the speed of light or if it would appear to not move at all, since he was also moving at the speed of light. That thought experiment triggered his theory of special relativity, and later, general relativity. Special relativity applies to the special scenario, where there are two frames of reference moving in a straight path parallel to one another at a constant speed. As soon as one of these conditions falls through, special relativity does not apply and general relativity is used to explain the motion. That means that general relativity is used for any situation where an object is moving in a curved path, accelerating, or being observed from a location that is moving in a curved path or accelerating.
I have a whole video on my channel about what the rules for those scenarios are, called general relativity.
So, what makes this case so special? Well, the answer comes back to Einstein's thought experiment. Classical mechanics says that Einstein should look over to the other light beam and it should not appear to be moving at all since they're moving at the same speed. But Maxwell's equations of electromagnetism say that that light beam should appear to move at the speed of light. So his thought experiment was at a standstill. Both classical mechanics and Maxwell's equations were very well accepted ideals, and it was hard to figure out which one was right. He eventually solved his thought experiment by proposing the equation E equals mc squared. So let's break that equation down. E stands for energy, m stands for mass, and c stands for the speed of light. So altogether, this equation explains the amount of energy that it takes to accelerate a particular mass to the speed of light. Now that seems relatively simple, but of course there's a few quirks. First is that when masses accelerate, they gain mass.
This is not noticeable on Earth. If you take a bullet train and accelerate very quickly, you will not notice yourself become heavier. That's because when these effects are studied on Earth, they are so minute that we can't measure them. But that's not the case in the cosmos. When stars or galaxies accelerate to near the speed of light, well, they noticeably gain mass, unlike on Earth.
So that means that as an object accelerates to the speed of light, its mass goes to infinity, and so does the energy required to accelerate it to that speed. This effectively means no mass can go the speed of light. It is not possible. So Einstein realized the universe has a speed limit that nothing can overcome. Light can only travel at those speeds because it does not have mass. An important side note here is that this doesn't apply when objects are really, really far away, because their relative motion may very well be the speed of light. If we look at a galaxy far, far away, it may appear to be moving at the speed of light because its relative motion to the Earth is the speed of light, even though its actual motion is not. Second, this famous equation ensues that mass and energy are interchangeable. Prior to that famous equation, it had not yet been proposed that mass had a relationship to the energy it possesses. The atomic bomb, which Einstein helped build, is very famous because it converts a very small amount of mass into energy, creating a very large explosion. So, how does this equation answer the thought experiment? Well, it says that light always moves at the speed of light, regardless of your frame of reference. So light will always appear to move at the speed of light, no matter what. When Einstein was imagining he was riding on a light beam, he would look over and the identical light beam would appear to move at the speed of light.
Those are the basic rules of special relativity, but of course there's another level. There's an implication of this theory that is very important.
Special relativity was the first time two things had been proposed. First, time relativity, and second, a connection between space and time. The relationship between space and time was introduced here, but mostly developed as a part of general relativity. Time relativity, however, is mostly grounded in special relativity. So time relativity is the idea that time moves more slowly when you are moving quickly. So if there was a 15-year-old who was traveling at 99.5% the speed of light for 5 years, when they came back to Earth, they would be 20 years old. Their classmates would be 65.
This is another quirk of the laws of high speeds. Time dilation happens every time we accelerate, but much like mass gain with acceleration, it's not very noticeable until the speeds become near the speed of light.
These laws govern the ways that many things in the cosmos work. When we see things traveling at the speed of light, we can deduce that they have no mass. When black holes shoot off jets traveling at close to the speed of light, we can understand more fully the content of the accretion disk. Accretion disks made up of mostly energy will produce jets that move at closer to the speed of light than accretion disks that have more mass in them. The laws of special relativity are also very important for understanding universe expansion. The universe is expanding faster than the speed of light, which is allowed because the actual expansion is of empty space, which has no mass. Another cool application of special relativity is in the GPS that's in your car or your phone. So GPS works by tracking distance by the time it takes to get from one point to another, and it does this using a satellite. That satellite is moving fast enough to cause a very slight time dilation. So the clocks on the satellite have to be set about 7 microseconds faster than clocks here on Earth. That doesn't sound like that big of a deal, right? Well, if we didn't calibrate them that way, that would be enough of a problem that the GPS would read 5 miles for a distance of half a mile after only 1 day of being miscalibrated.
All of these applications are important, and there's a lot we wouldn't understand about black holes, cosmic material, and dark matter without the theory of special relativity. Special relativity is an amazing theory. Thank you so much for joining me.